LeCun's recent declaration that LLMs will be obsolete within 5 years has sent shockwaves through the AI community. This provocative stance from one of AI's founding fathers challenges our assumptions about the future of artificial intelligence and demands our attention. Yann LeCun isn't just another voice in the AI debate. He's Meta's chief AI scientist, a Turing Award winner, and one of the pioneers who laid the groundwork for today's AI revolution. His contributions to convolutional neural networks in the 1980s enabled breakthroughs in image and video understanding that we now take for granted. When someone with this level of expertise and influence makes a bold prediction about AI's future, the tech world listens. What makes LeCun's position particularly fascinating is the paradox it presents. Here's a man leading AI research at Meta, which has invested heavily in LLMs, including their popular Llama model that recently hit 1 billion downloads, yet he's publicly declaring this technology will be obsolete within 5 years. It's like the chief architect of a skyscraper announcing that tall buildings are fundamentally flawed while his company continues building them. Why LeCun believes LLMs are doomed. Yann LeCun's skepticism about large language models stems from fundamental architectural limitations that he believes cannot be overcome through incremental improvements. At the core of his argument is the mismatch between how LLMs process information and how intelligence emerges in biological systems. Disembodied intelligence in a physical world, LLMs operate entirely within the realm of language, a secondary representation of reality while remaining oblivious to the physical environment that shapes human cognition. A human child develops an intuitive understanding of gravity, object permanence, and spatial relationships through 16,000 hours of visual experience in their first 4 years, processing approximately 10 to the power of 14 bytes of sensory data. In contrast, even the largest LLMs trained on 30 trillion tokens, equivalent to 10 to the power of 14 bytes, lack this embodied grounding, creating what LeCun calls an understanding gap that no amount of text can bridge. This disconnect manifests when LLMs struggle with simple physical reasoning tasks that any toddler could handle, like predicting whether pushing a glass near the edge of a table will make it fall. The fragility of tokenized reasoning. The autoregressive nature of LLMs predicting one token at a time introduces compounding errors that undermine reliable reasoning. Recent studies reveal that these models exhibit premise order bias, where changing the sequence of information in a logic problem drops accuracy by up to 34%. Unlike humans who maintain mental representations of concepts, LLMs process language as discrete tokens, making them vulnerable to surface-level statistical patterns rather than deep understanding. When asked to solve analogies like, if Alice is taller than Bob and Bob is taller than Charlie, who is shortest? LLMs often fail despite the straightforward logic, revealing their lack of persistent symbolic representations. Memory without context. While LLMs demonstrate impressive recall of factual information, their memory lacks the continuous, associative quality of human cognition. The transformer architecture's attention mechanism creates what researchers call contextual amnesia. Each query resets the model's working memory, forcing it to reconstruct context from scratch. This contrasts with biological intelligence, where memories form through synaptic plasticity in neural circuits shaped by lived experience. LeCun notes that current architectures cannot achieve the persistent memory required for complex tasks like maintaining a coherent conversation over weeks or planning a multi-step project. Planning in abstract spaces. Human planning occurs in latent spaces, abstract mental representations that allow us to simulate outcomes without physical trial and error. LLM's token-based architecture confines them to language space, making even simple planning tasks computationally intensive. Princeton researchers demonstrated this limitation by testing LLMs on Tower of Hanoi puzzles, where models required 10 times more training examples than humans to achieve comparable performance. The challenge intensifies with real-world planning scenarios involving uncertainty, where LLMs struggle to adjust plans dynamically when conditions change. LeCun's critique extends beyond technical limitations to question the very paradigm of intelligence through language. Tokens are discrete proxies for reality, he argues, noting that language constitutes less than 1% of human sensory input, yet dominates LLM training. This over-reliance creates systems skilled at manipulating symbols, but blind to the continuous, high-dimensional reality those symbols represent. While some researchers propose combining LLMs with external knowledge graphs or verification systems, LeCun maintains these are stopgap measures that fail to address the core architectural constraints. His proposed alternative world models built through joint embedding architectures aims to replicate the human capacity for mental simulation, enabling AI systems to reason about physical cause and effect relationships directly in latent space. The data bottleneck that can't be overcome. Perhaps LeCun's most compelling argument concerns the fundamental data disparity between humans and machines. Current LLMs are typically trained on approximately 30 trillion tokens, which is roughly equivalent to 10 to the power of 14 bytes of information about the total amount of text available on the internet. Reading this volume of text would take a human roughly 400,000 years, yet a mere 4-year-old child, having been awake for only about 16,000 hours, has processed approximately 10 to the power of 14 bytes through vision alone. In just 4 years of life, a child processes as much visual information as text that would take 400,000 years to read. As LeCun succinctly puts it, we're never going to get to AGI by just training from text. It's just not happening. The alternative, world models and JIPA. If not LLMs, then what? LeCun believes the future lies in world models and a specific architecture called Joint Embedding Predictive Architecture, JIPA. World models, as LeCun explains, are internal representations of how the physical world operates, similar to what we all develop in our minds. When you know that pushing a water bottle from the top will make it tip over, while pushing from the bottom will make it slide, you're using your internal world model. These models allow us to understand and predict physical interactions without conscious calculation. The JEPA architecture is LeCun's approach to implementing these world models in AI systems. Unlike generative models that try to predict every pixel or token, JIPA operates in abstract representation space, comparing representations rather than raw inputs. This gives it the flexibility to ignore unpredictable or irrelevant details and focus on meaningful patterns, improving training efficiency by 1.5 to 6 times compared to generative approaches. Meta has already released several iterations of JEPA models, iJIPA for images, MCJEPA for multitasking, vJIPA for video. These models learn by predicting missing or masked parts of inputs in an abstract representation space rather than at the pixel level, allowing them to develop more semantic understanding. The latent space advantage. What makes world models fundamentally different from LLMs is their ability to operate in what LeCun calls abstract mental space, or latent space. When we reason, when we think, we do this in some sort of abstract mental state that has nothing to do with language, LeCun explains. He provides a simple demonstration. Imagine rotating a cube 90 degrees in your mind. You don't perform this visualization using language tokens. It's a purely mental simulation. Even animals without language capabilities, like cats, can perform complex planning tasks, such as calculating jumps onto furniture. They're reasoning in abstract space, not language space. This is the kind of thinking that world models aim to replicate. The race for AMI, not AGI. Interestingly, LeCun dislikes the term AGI, artificial general intelligence, preferring instead AMI, or advanced machine intelligence. His reasoning? Human intelligence isn't truly general. It's highly specialized, making the general in AGI something of a misnomer. LeCun believes that systems capable of learning abstract mental models of the world and using them for reasoning and planning could emerge at small scale within 3 to 5 years. But he's also cautious about timelines, acknowledging the long history of over-optimistic predictions in AI. Historically in AI, there's generation after generation of AI researchers who have discovered a new paradigm and have claimed that's it. Within 10 years, we're going to have human-level intelligence. And that's been the case for 70 years. Industry shifts already underway. While LeCun's predictions might seem radical, there are already signs that the industry is moving in this direction. Google DeepMind recently introduced Gemini Robotics, a model designed specifically to bring AI into the physical world with embodied reasoning, the human-like ability to comprehend and react to the physical environment. NVIDIA announced their Cosmos platform at CES 2025, designed to teach machines how the physical world works using world models. Companies including Uber, Figure AI, and Wabi have already signed on to implement this technology. Even researchers outside these major companies are exploring world model approaches. The Dreamer algorithm, for instance, has shown promise for reinforcement learning using world models, enabling robots to learn from small amounts of interaction by planning within a learned world model. Are LLMs really doomed? Despite LeCun's persuasive arguments, not everyone in the AI community agrees that LLMs are approaching a dead end. Some researchers argue that LLMs could develop self-reflexive error correction through expanded reinforcement learning, allowing them to assess their own reasoning quality. There's also the question of whether world models and LLMs are truly opposed approaches or potentially complementary ones. Could future systems integrate the token-based strengths of LLMs with the continuous understanding of world models? What's clear is that LeCun's criticisms touch on real limitations of current LLM systems. The question isn't whether these limitations exist, but whether they can be overcome through evolution of the current paradigm or require the revolutionary approach LeCun advocates. What are your thoughts on these? Drop down in the comments and subscribe for more AI-related news and updates.